In most research projects, when collecting data from a sample, the goal is not only to describe that group of individuals, but to use the information collected to draw conclusions about the entire population. This is not a simple interpretation of the result. It is a systematic process that follows the rule of statistical inference. In this presentation, we will discuss how to estimate the mean of a variable for the entire population after computing the mean for a specific sample. For instance, let's say that we're interested in estimating achievement motivation for first-year college students. To do this, we must first select a random sample of students, administer a motivation scale, and then compute the average score for the entire sample. Based on this average score, we can then make an inference about a motivation of the entire population of first-year college students. Before making any inferences about the population mean, we must first make sure that we meet certain requirements. First of all, our sample must be randomly selected. Second of all, we must know that the variable that we're interested in has a normal distribution in the population. And third, although we don't know the population mean, we must know the population standard deviation for that variable. These conditions are very difficult to meet in a real-life situation, especially in social science research. There are other procedures that need to be followed when these conditions are not met, but for now, let's just focus on the best-case scenario when all these assumptions are met. Let's use our example to illustrate how to estimate a population mean based on the sample mean. Let's say that we selected a random sample consisting of 400 college students, and the mean score for our sample was 80. This mean of 80 is a statistic, a value that we can measure directly based on what we observe in the sample. The population mean, however, is a parameter because we cannot measure it directly. We can only estimate it based on what we observe in the sample. So now that we know that the sample mean is 8, what can we say about the population mean? Can we say that the population mean is 80 as well? No, this would be very unlikely because if we select a different sample, the mean will be slightly different, maybe 81 or maybe 78. So how can we make an estimation about the population? To do this, we need to know the standard deviation of this variable in the population. The population mean for a certain variable is estimated by computing a confidence interval for that mean. If we could select several random samples, we could see that the mean for that variable would be slightly different from one sample to another. Therefore, when we estimate the population mean, instead of providing only one value, we specify a range of values or an interval within which this mean is likely to be located. To obtain this interval, all we have to do is to add and subtract a margin of error to the sample mean. This way, we obtain the upper limit and the lower limit of our confidence interval. The confidence interval may be wider or narrower, depending on the degree of certainty or estimation precision that we want to have. For instance, in our example, the sample mean was 80, and let's say that we want to have a confidence interval of 95% for our estimation. In this case, the margin of error is 3.92, and we'll discuss a little later how to obtain the margin of error, but let's just focus now on how to obtain the confidence interval. So, if the margin of error is 3.92, all we have to do is to add this value to the mean of 80 to obtain the upper limit of the confidence interval, and then to subtract this value from the mean to obtain the lower limit. For our example, the upper limit is 83.92, and the lower limit is 76.08. Therefore, a 95% confidence interval is between 76.08 and 83.92. When we have to explain the meaning of this confidence interval, we can state with 95% confidence that the population mean on this motivation scale is somewhere between 76.08 and 83.92. Now that we have a general idea of how confidence intervals are obtained, let's see how we can obtain the margin of error. The margin of error depends on the degree of confidence that we want to have for our estimation. Typically, these levels vary between 90% to 99.9%, but it is up to the researcher to decide. The level of confidence is represented in the formula by a lowercase z with a star, and we call this number z star. We will discuss more about how to choose the confidence level. Let's just focus on the formula for the margin of error now. We also need to know the standard deviation for our variable in the population. You must be very careful here not to use the standard deviation from the sample. This is not the sample standard deviation. It is a number that is known from prior research. Another number that we use in the computation procedure is the sample size. So, for our example, z star is equal to 1.96. Now, you may ask yourselves, where does this number come from? This is the value that we always use when the confidence level is 95%. For other levels of confidence, such as 98%, z star is 2.326, and for 99%, z star is 2.576. These are standardized scores and are based on the normal distribution, and you can find them in the last row of Table C on the very last page of your textbook. In our example, the population standard deviation was 40 and the sample size was 400. So to obtain the margin of error, all we have to do is to divide 40 by the square root of 400, which is 20. And then we just multiply z star by the result of this division, which is 2. So 1.96 multiplied by 2 is 3.92. So our margin of error is 3.92. Now let's put all the information together in one formula. We know that the confidence intervals are obtained by adding and subtracting the margin of error from the sample mean. We also know how to compute the margin of error using z star, the population standard deviation, and the sample size. So now we can put it all together into one formula that we can use directly when we need to compute a confidence interval. Using this formula, try to compute a confidence interval for the same population mean with a confidence level of 90%. To do this, you must find the value of z star for this confidence level using Table C in your textbook. Now, you already know how to compute a confidence interval, but you may be wondering where this formula comes from. Well, as I mentioned before, we never know the true value of the population mean. We can only approximate or estimate this value. The best way to do this is to select a large number of random samples of the same size from the population. The mean from each random sample will be slightly different, but if we compute an average of all the sample means, this value would be the population mean. For instance, the mean of our sample was 80, but if we select another sample, the mean might be 78 or 83. If these means are represented graphically, they would have a normal distribution. The mean of this distribution is the same as the sample mean, but the standard deviation of this distribution is equal to the standard deviation of the variable in the population divided by the square root of the sample size. This is why when we try to estimate the population mean, we are using the standard deviation divided by the square root of n instead of the simple standard deviation, because this formula represents the standard deviation of the distribution of many sample means. Of course, when working with real data, selecting a very large number of random samples is simply not feasible, but this is what would happen if we were able to do this. Because all the means from random samples have a normal distribution, We can also use the 68-95, 99.7 rule to estimate the values within which the population mean would fall. To obtain the 95% confidence interval, all we have to do is to add two standard deviations above and below the sample mean. Therefore, if we add two standard deviations to the mean, we obtain the upper limit of the 95% confidence interval, and if we subtract two standard deviations from the mean, we obtain the lower limit of the 95% confidence interval. Notice that with higher confidence levels, the interval also gets larger, so we have less precision. As we can see from the 68, 95, 99.7 rule, the 68% confidence interval for our example is between 78 and 82. The 95% confidence interval is approximately between 76 and 84. And the 99.7 confidence interval is approximately between 74 and 86. Therefore, the larger the confidence level, the larger the interval. There is a trade-off between the two. If we want to be very certain that our interval includes the population mean, we have to extend the interval, so we have less precision. For intervals that are not specified in the 68, 95, 99.7 rule, we can use Z star to obtain the upper bound and the lower bound of the interval. As you might have noticed, Z star provides more precise estimates, whereas with the 68, 95, 99.7 rule, the values are rounded. The confidence interval depends on how large is the margin of error. The larger the margin of error, the larger the interval. As I mentioned earlier, the larger the confidence level, the larger the confidence interval. If we want the interval to cover a very large proportion of possible values, like 99.9%, the interval will also be large. Z star is the part of the formula that represents the level of confidence, so as Z star increases, the interval also increases. The margin of error also depends on the standard deviation of the variable and the sample size. The standard deviation is the numerator of the fraction, so the larger the standard deviation, the larger the margin of error. The sample size is the denominator of the fraction, so the relationship is reversed here. The larger the sample size, the smaller the margin of error, and therefore the smaller the confidence interval. In conclusion, the confidence interval represents the chance to capture the population mean if we measure the variable many times with different samples of the same size. So theoretically, when reporting a 95% confidence interval, for instance, we should say that we are 95% confident that all possible samples of a certain size from the population will result in an interval that captures the population mean. However, most of the times, researchers abbreviate this explanation and say that they are 95% confident that the population mean is located within a certain interval. In summary, when we have to estimate the population mean based on the sample mean, there are 4 steps that need to be followed. First, we must formulate our research question and identify the parameter that we need to estimate. Before computing the confidence interval, we must make sure that we meet the assumptions on which this procedure is based. We must have a random sample, the variable must be normally distributed, and we must know the standard deviation of this variable in a population. Only after we completed these steps, we can proceed to compute the confidence interval.